And to take us up to our afternoon tea break, I would say coffee, but this is the UK. We have my next door neighbour, actually, up at King's Buildings. So this is Professor Albert Simeoni, who has been at Edinburgh now for 8 to 10 months, something like that, who is our new BRE Chair of Fire Safety Engineering. And he's going to talk to us about his particular specialism, which is wildland fires.
Thank you, Luke. So, by the way, this is a nice photo. That's what we are doing with my students and colleagues in research. It's nice, isn't it? It's an experimental fire we did on last March in New Jersey, in a pine forest in New Jersey. But don't worry, I will put some color in my talk. So basically, what I want to do today is to convince you that wildland fires is a fire problem. It's the same kind of problem we are having in the fire community, and you need to have the same skills. But also, it's much more complicated for many of its aspects. You take all the problems which were cited in the 2 previous talks, so all the problems of the warehouse fires, or all the problems of the flammability of fuels, and you add an order of magnitude and you have wildland fires. So we are trying to figure out things and trying to have some quantities that we can use in a very scientific way. So just I played the game like everybody, so asking the 3 questions. So the first one was, where are we? And so that's the magnitude of the wildland fire problem. You know that if you look at the statistics of the Food World Organization, basically Africa, South America, and Asia and Southeast Asia are burning much more than California, than Greece or Portugal. But that's where people are, and usually people of a certain wealth, certain level of wealth, and that's where the challenge is. When it's burning in the forest, people get overexcited. For instance, oh, it's burning in Yellowstone. You can have, for such big fires, so change in policy in management of forests, but people forget. And they go and they visit and they see a few trees burned, or a lot of them, but they move on. But when your life is destroyed, that's another problem. So you will notice also, and that's a point that I want to make, look at the vegetation here. Pretty in good shape. But the houses are all burned. So for a lot of places, wildland fire is a wildland-urban interface fire and can become an urban conflagration fire problem. I mean, when you have cities burning, still burning in some places in the world, in the Western world, we designed our cities, and we'll talk about that later, not to burn. So that's exactly the same problem. Basically, the fire is hitting a development, and then it's spreading through the development, even not touching the vegetation. So I couldn't avoid to put that happened in the highlands. So the context is changing, and in a very opportunistic way for me, it happened 2 weeks before my interview for the position. So I was very, very happy. If you look at the size of the fire, so that this little town is here, so it was pretty big, very unusual in the highlands, and like all the problems were coming. What can we do with that? We are not used to fight these fires. Hopefully this is Scotland. So the winter, then the fire just stopped, and the day after it was raining, so the problem was solved. So if you look at the most expensive fires in US history, because as Patrick was talking about the statistics, and there are countries you have very good statistics. I was desperate yesterday night to look for statistics in Portugal and Greece in terms of cost, and I found one. But for the US, we have a lot of them. So that's the number of the most expensive fires in US history. The first one, which is overshadowing all the others, is 9/11, the Twin Towers. But the fourth one, and that's adjusted loss in 2012 US dollars. So you see the extent of the problem here, and you see that there are fires which are usually and very often wildland urban interface fires, and they are very, very expensive. So I have to balance that with the fact that it's not happening every year. So if you compare that with a lot of smaller fires happening every day, you'll balance the cost differently. But it's still pretty striking to see that on the first 11 fires, you have 5 wildland or wildland urban interface fires. The Auckland fire was pretty small, but it burned a lot of houses. And also, if you're looking at the dates, except for the Twin Towers, I looked at the fires, and you had the Great Baltimore Fire, the Great Boston Fire, which were at the beginning of the 20th or at the end of the 90th century. So you're looking at the dates after 2000, there are 4 fires. So it's a tendency which is going on. The wildland urban interface is growing in many parts of the world, not only in the US, in the Western US. It's growing in Europe, it's growing in Asia, it's growing in South America. I'm sure you've seen in the news the fire in Valparaiso. That's another example. And so I'm just putting other numbers for fires which are well known. The Black Saturday fires in Australia, and the only number I could have for the Greece wildfires, because there were more than one, and they were called the Great Peloponnese Fires. That's the cost. And I didn't put the loss of life, but for some of them, for instance, in Greece, it was 84 people died. And in Australia, 173. So also the money to deal with this problem. If you're looking at the numbers, so it's approximately $500 million spent in the US on fuel treatment. And from the body, the John Fire Science Program, which is funding fuel treatment and funding research on fuel treatment, they are stating themselves that we don't really know what we are doing. So let's take the example of Australia to talk about the way it's changing. So the 173 fatalities, it's the highest number in modern Australian history. The size of the fire, the number of buildings, it created a lot of discussion about the way to evacuate or to ask people to stay and defend. There were some dramatic cases. I remember when I was visitor in Edinburgh, I was lucky to be a visitor here before joining. We had a dentist coming and doing a talk on that. And he was telling us pretty dramatic stories of people totally trapped and unable to evacuate. And families which were just all killed. But if you're looking at the conditions, you realize that for these days, that was the worst bushfire weather conditions ever recorded. So high temperatures, high winds, low levels of humidity, so something is going on also. So it's a combination of first socio-economic changes with the spread of the wildland urban interface, with the fact also that the stakes are higher now in the suburbs. Because if you're taking, the suburbs of Los Angeles, for instance, the nice suburbs, people want to live close to vegetation, but also have these people, wealthy people, with health problems. And then you have a hospital, and this hospital is doing very, cutting-edge surgery, very expensive, and if a wildland fires is closing the hospital, which happened for 2 weeks, it's a very big economic loss. So even the activity is moving to the place where there is a fire risk. So then, talking about these extreme behaviors, and the Black Saturday fires in Australia are still the topic of studies to understand. It's called a firestorm, how the firestorm developed and how certain fires converge, apparently were sucked toward each other and converge, and they converge when they were houses. And so you have the fire eruptions. This image is from Corsica. And so the surface you can see here, that's quite a big electric line. So quite a big post, it's around 10 meters. At the same time, there was 6 hectares of vegetation burning. And it was the closest phenomenon that we observed, we could relate in fire science with the trench effect and the King Cross station fire. So they are self-accelerating fires, and on this fire, 3 firefighters died, and 5 were severely injured. To incapacity. So you have crown fires. That's a really big problem. That's very usual in many places. But the way the fires are burning, the ways the fires are spreading is changing too. For instance, crown fires in the Far East of Russia result in a forest not regrowing after the fire, which is a new thing. So you have entire patches of forest, it's not just deforestation, but which disappear because of violent fires. This combination of weather and the big fire plume, which is foresters or firefighters have the tendency to say a very large fire is creating its own weather. In the US, for very, very large fires, you can have even storms after a fire because of this big plume and the big cloud which is created. And the spot fires or the firebrands are a very big problem. The image I showed you about California, the NIST did some field feedback studies, and it's very likely that the houses are ignited because they are ignited by flying firebrands, and then a house burning is producing more and it's spreading like that. It's not, how in a suburb, it's very unlikely that the main cause of spreading is from direct contact of flames or house to house. So another problem which is very important and was understated for quite a long time are peat fires. When the peat is accumulating when there is a lot of water. But now with the climate change and the extended periods of droughts, the water table is going down, and then it's a fuel which is burning very well, especially smoldering. And smoldering, it's nasty. It's a lot of smoke. You see it here. It's nasty gases. It can stop the economy. So it's a very, very big problem too. And by the way, there was a very interesting article from a Russian scientist saying that the peat fires happen in Moscow because at highest political level it was decided to cut the fire prevention budget by a factor 4. And so, and they were explaining the correlation, and apparently this person is still in the US. So now it's more about where are we? So I think I put the context, but what do we have to face these kind of problems? So the first studies which were done is like to evaluate the risk, to know if you want to prevent or to fight the fire, you need to know the days where you are the most at risk. And so we have risk indexes. They are working pretty well in Canada, US, and Europe. But now we have these extreme climate events, and they are not working very well anymore. Basically, if you think about like the big fires in California, they always happened. The big fires in the south of Europe, they always happened. But now they are happening every year, and having on your scale of risk, extreme risk for the whole summer doesn't really help. So we lack resolution because there is a shift in the scale. Fire spread. So we have two types of models, and I will develop that very soon. So you have semi-empirical models which are applied at landscape scale, and some CFD models, so like the one at the Los Alamos National Laboratory at landscape scale, but running for weeks on the supercomputers of Los Alamos, or something more at the wild and urban interface scale, more like really the interface, for instance, between a few houses and a forest. And this is a module in FDS with all the drawbacks. We heard about FDS in the fact that for the moment, it's changing, but for the moment, you can only simulate on your PC. So, and these models, whatever the models, and I could speak for hours about the limitations. The problem we have is that they are not doing a very good job at quantifying. So basically, they were developed quite a long time ago for the empirical models, and more recently for the CFD models, but still we can't quantify. And then we have fire safety in general, so the measures we take in fire safety. So you use a lot of the empirical knowledge. Some analytical approaches with some simplified modeling to get, for instance, the radiative impact of a fire on firefighters or even on structures. We have standards and codes, NFPA, International Code Council, ASTM. We have some best practices, fire-wise in the US, fire smart, fire safe, even regulation, for instance, in France. You have to clean around your house. You have to make your house safer if you are at the wild and urban interface. But the problem we have is that they are not based on very strong scientific basis. And there is a gap here because even the quantification we provide for the standards and codes, if it was working so well, we would not lose like thousands of houses every year in wildfires. So what is so difficult with wildfires? And I will be very fast with this slide. But basically, it's the different scales. Okay, when you stop the warehouse to a third of that, okay, we have to continue to the fire scale, and I didn't even put the atmospheric scale. And every scale has some influence. So we simplify, but we are always valid for a certain range, and we are always finding very strong limitations. So that's a very tricky phenomenon to study. But it doesn't mean that we cannot transfer knowledge to the end users. I mean, we are engineers, so it's fire safety engineering. So, for instance, these fires were reproduced in Portugal at the lab scale. We don't really know what is the prevailing effect. I have my opinion, but for the moment it's not scientifically proved. But we are able to produce a guide for firefighters, at least identifying which are the dangerous configurations where they should avoid sending people. Another one on peat fires. There were experiments conducted in Edinburgh, and so you can get some estimation of the severity. The severity of the fire is how the fire is impacting the environment after the fire. So how it is basically killing everything, and how long the environment will take to recover afterwards. And it has big implications: floods, erosion, and also the vegetation cover. And also some link with the emissions, because a big problems we have in terms of society with wildfires. It's not only the fact that it's burning; you can burn your house, and it's very, very ugly behind your house when it's burned. It's also that it's emitting smoke. There is an impact on the environment. There is an impact on human health too. The Moscow fires, the rate of heart attack and asthma just skyrocketed during the Peat Fires in Moscow. So how did we get here? So there are different studies, but what I really want to point out here is that we really have a knowledge gap, and we really, in a way, hit a wall at some point in wildfires. So in the US, you see that the program started kind of 100 years ago. In Canada, it was very soon after. In Australia, in the 60s. Then, this one is Philip Thomas at the Fire Research Station. Interestingly, fire spread in heather was studied first in the UK for Europe. There were a lot of studies developed in USSR. We learned about that after the collapse of the Iron Curtain. And also, there are different approaches. So in the US, Canada, and Australia, it's mainly forest services and public bodies. The university involvement is growing, but still. And in Europe and Russia, it's mainly conducted in universities. So there are different approaches. So you find the CFD models were first developed in Russia and in Europe because that's an academic problem and it was taken by the university. But in terms of modeling, if we move on, so you have three big ways to approach it. So you have like the Canadians, they use a very, very simple index. These parameters are fuel dependent, but basically it's giving you an initial rate of spread. And basically it's only for the risk index. They don't want really to know where the fire will go. You see Canada, and you know the population of Canada. So they will not fight every fire. They don't have the same whale-underban interface problem, even if it's a problem, but it's not like California. So basically what they want to know if they have to attack the initial fires, they want to know if there is ignition, which will be mainly by lightning, how the fire will initially spread. So that's very empirical. You have Australia, it's even very, very empirical too, but in some parts of Australia, the conditions are quite constant. Vegetation, the weather is quite constant, so it's working quite well. It's for grassland, they have a lot of grass, and for eucalyptus forest. And you still have foresters in the field in Australia which are using these discs. And with a certain level of success, like for the mainstream fires, but like the 3% fire you cannot extinguish, like the Black Saturday fires, you cannot use these discs. And then the semi-empirical modeling, which is basically a one-dimensional model, steady state, that's the rate of spread, that's basically the energy transferred by the fire front to the fire, and that's the energy absorbed or necessary to ignite the fire. So this one is very simple, but then you can put it, because it's very simple, you can solve it very quickly, you can put it in a very big model, make extrapolation about the 2D development of a fire. You're saying that the fire front would be an ellipse anyway, and you are able to run these kind of models. This model is from 1972, which is a very good year because I was born in 1972. But beyond that, we don't have an operational simulator beyond that. So that means that for 40 years, we were not able to do much better than that. I mean, the simulator is from 96, and we are still incrementally improving it, but the basic model didn't change. So then you can go for physical modeling. That's something I worked on during my PhD. And then if you have to describe oil and fuel, which is very, very porous, you have to adopt a multi-phase approach, but then you have the problem of physical modeling, and we were talking for flammability. Nico was saying that you need 37 parameters, and here, if you want to describe the interaction between the gas phase and all the solid phases, you have all the interface relationships with submodels, plenty of parameters. You want to close your model, and it's a nightmare. So it's a very difficult approach. But still, this approach was implemented in FDS. And so that's WFDS, and this one is like something like 200 meters by 200 meters, and it still has some capability, but not beyond this size. There are other modeling we can use, other approaches like simplified physical model or fire-atmosphere interaction for the very large-scale phenomena, but we are hitting a wall here, because with these simplified models, you have less parameters, you have the relevant ones, but one in fires is there are so many different cases that you don't need to develop one model. You need to develop a family of models. And then you need to be sure that your models are appropriate, and that's difficult. I will go very quickly on the experiments, but all this work I told about modeling, but is pushed by also a lot of experimental activities. You know the problem of increasing the scale of your experiments and having no control at all at the end. So that's a trade-off. Here you have maximal control, but you don't have realistic conditions, and you are trying to reach the scales, and it's very difficult. We have exactly the same problems. So where are we going? And I will finish very briefly on that. I think this wall that we are hitting, and we are working very hard to try to go beyond that, it's because if we want to go beyond this semi-empirical models, we really need to understand the fire fundamentals. So combustion, how vegetation is burning, what is the fire dynamics, and we have to do that in a changing environment. So the only answer for wildfires, I think, is to link with other research fields to understand emissions, forest dynamics, which is changing the fuel, for instance, and the regimes, and fire science. I mean, that's why I visited first Edinburgh. For the little story was that we were hitting this wall, playing with the very complicated model I worked on during my PhD, on the very simple models, and we didn't understand what we were doing. So we thought maybe there are other places and other communities where tools are already used to understand fire, and we went to visit Edinburgh and propose the collaboration. So very quickly, better understand the fundamentals, so that the perfect example, using something which is used in fires. So I will move on. Oh, by the way, Nico, PMMA is not life, it's pine needles. Okay? Ignition, behavior, and exactly, so that's why I will go very quickly. In a more complicated context, that's all. We try to simplify it too, but we have the same kind of things. We are doing experiments controlled in the lab. We simulate with the multi-phase formalism I told you before with the University of Marseille. We put it in fire foam to have like a more flexible, more fundamental problem to study. We're also looking at the structural part because we just want the time to ignition. We don't want to simulate in 3D the houses. It's enough to simulate the fire. So other things we are doing is, for instance, to study the drag forces, which is very important in wildfires because vegetation is very porous. We are not at the stage of introducing the fire. We are looking at forests, and we did quite well with that. Now we are looking at the wildland-urban interface, and it's very tricky because it's the flow around and through a tree, which is much more difficult, and very, very few people studied that. And then we need that. That's our experiment. What you've seen in my first slide was the result of the experiment. But we need that. And that's very difficult because that's the scale where we don't control. And you can look at this tree. Wow, when we saw that, we were all jumping, auto-ignition of the trunk. And so that's basically, you see our testing, very simple thermocouples, thin skin calorimeters, but we need to have like this reality check. We need to have like an estimation of the quantities. We cannot even dream about the projects like the large, the tall building projects where you have a big room and you put 1,000 thermocouples. How can we do that? Here, we put 50 and we really suffered. We had to dig the data loggers, and it was very difficult. But we have some quantities, and we need this reality check to be able to develop our program in the lab with the good quantities and to be really able to understand what's happening at the basic level to feed our sub-models and to close our more complicated models, which allow us, like Lou was saying, to investigate really what's going on at this level and also to test the different scenarios. So that's just the end, the last slide. So I think it's summarizing the statement I just did. But basically in wildfires, doing full testing is not a solution. I don't think we can really, toast all the forest we have around I mean, the pine barrens, by the way, we are burning like that because that's the way the ecosystem is working. They have these fires, so they prefer to do prescribed burning and to burn them when there is a lower risk. So we can burn trees. There are very few places where you can burn trees. Usually people don't like that. Firefighters don't like that. And we like that, but it's very funny. I was at a conference, we had ecologists and fire scientists in Russia, and they were bringing us on a fire, and we were all looking at the fire scars saying, wow, that's a wonderful fire, it burned so many trees, look how intense it was. And we had the ecologists telling us, no, don't walk here, there is this moss or this fungus, it's very, very... So we don't have the same perspective, we like to burn things. But what we have to do, which is a bit different in wildland fires, applying the same approach, is that we need to be very careful when we do the field experiments. And even this fire, which is a crown fire, is not comparable to the firestorms. How do you instrument a firestorm? And that would be another debate. I will leave you with that, talking about sensor networks, dropping them from helicopters. The day I will have a research program of $5 million a year, maybe I will do these kind of things. Thank you.
Albert, do we have any questions for Albert? Jonesing for coffees.
If you would have to state what the end goal of the research is, would it be urban planning or would it be more how to combat the fires?
Yes. That's a good question, actually. Because for 97% of the fires, and you can apply these statistics almost everywhere, except for remote places like the north of Canada or the north of Russia, they are extinguished. I mean, we cannot come as scientists and tell the firefighters, we learn you how to extinguish fires. They know to do it very well. For the 3 other percent, even in the US with the big means they have to compare to other countries, they don't extinguish them. So I believe more in the planning, in the prevention, than in the firefighting by itself. You can improve the firefighting. You can give like some recommendations to be more efficient, like don't drop water here anyway, it's useless, the fire will blow up and it will be useless. But the real contribution of that is really to bring tools to help people to make decisions where the high stakes are, and it's when fire are out of control at the wildland urban interface. I think that's kind of a new frontier in fire science.
Seems like a good place to stop and have a coffee. So we'll go downstairs, we'll have coffees, and we'll herd you back up at the appropriate time.